So, hello everyone, my name is Mahdokht Montazeri. I'm a PhD student in environmental engineering at Northeastern University. And today I'm going to talk to you about a project I've been working on for a while, which is a review on life cycle assessments of prioritized renewable chemicals and their GHG reduction potential. This project looks into different LCAs conducted for different renewable chemicals, and I'm going to specify further in my slides that which chemicals are included, and it's a collaboration between Northeastern University and University of Pittsburgh. I'm going to start with an overview. First, I'm going to talk about the total production of fossil-based and bio-based fuels, chemicals, and polymers. And I'm going to talk about the RFS regulation regarding biofuels and how we use the thresholds that has been developed by RFS for our own study. And we're taking the same approach that EPA did for conducting this regulation for the renewable chemicals. And I'm going to show you a case study for bioethylene as one of the renewable chemicals. I'm going to introduce prioritized bio-based chemical or the bio-based chemicals that we considered in our study. I'm going to show the categorical variables in our literature review, an example, simple illustration of selected cases, and the study assumptions that we had, results, conclusions, and next steps. So in our daily lives, maybe the most important categories of product that we use are fuels and chemicals or polymers. On fuel side, we have total production of 131.3 million tons of oil equivalent in 2013. And on the other hand, we have total production of biofuel, which is equivalent to 82.1 million tons of oil equivalent, estimated in 2012. On the chemicals and polymer side, we had total production of 330 million tons per year based on fossil-based sources. So the top chart shows the fossil-based sources. And we had total production of 50 million tons per year for bio-based chemicals. These numbers are global production, so it's worldwide. So we know that EPA did RFS program and started to look into different types of biofuels, and the RFS 2, for example, mandated 36 billion gallons of biofuel production by 2022 and GHG reduction of at least 20% for bio-based fuels. And then it further specified the biofuel reduction potential based on the categories that they are coming from. For example, the biofuel from non-corn feedstock should mean at least 50% reduction in GHG emissions compared to regular fuel, while the biofuels from, for example, biomass-based diesel should meet the 50% reduction again, and the biofuels from cellulosic and agricultural waste should meet at least 60% reduction potential. So based on these rules and regulation, we now know that what is going to be called as renewable fuel. For example, the main criteria that should be met is that, for example, what is this biofuel is coming from, so this much of GHG reduction should be met. But we don't have these strict rules and regulation for bio-based chemicals, so what is considered as a bio-based chemical. So what we're trying to do in this study is using the thresholds has been defined for biofuels for renewable chemicals. So we want to see what if we consider 50% GHG reduction potential as our basis for bio-based chemicals, how many of the important building blocks that we use daily going to meet this 50% reduction target. I'm going to show you a case study of bio-based ethylene done by Dan Posen, who's sitting here. He conducted an LCA and looked into production of LDPE from sugarcane, switchgrass, and corn, and compared the results with the fossil-based counterparts and wanted to know if the bioethylene coming from these sources can meet RFS 2 target reduction potential. So these are the results from Monte Carlo analysis, and you can see the first figure, the top figure, shows the probability density versus GHG emission for 1 kilogram of LDPE, And the bottom one shows the same for 1 kilogram of ethanol, which is equivalent to this much of energy. And then he compared the results with the RFS target. So here you can see corn-based ethanol and LDPE, sugarcane-based ethanol and LDPE, and switchgrass-based. So for corn scenarios, this 20% target reduction was specified by RFS, and you can see for most of the scenarios, both LDPE and ethanol can't meet this target potential, while for sugarcane and switchgrass, they can meet 50% and 60% target potential that was specified by RFS. So we're trying to do the same analysis with the 50% threshold that we chose and expand this to a category of renewable chemicals that I'm going to show you here. So we chose our chemicals based on 2 studies that has been published by Enrel in collaboration with PNNL. So they tried to screen out feasible chemicals that can be produced from sugar and lignin. So the first volume of this study looks into the sugar-based chemicals, and these are the building blocks that they reported based on the sugar components of biomass. And the second volume looks into feasible chemicals can be produced from lignin. And these building blocks are the chemicals that they introduced. So we tried to find the LCA analysis, looked into these renewable chemicals, and compared the GHG reduction potential between the bio-based sources and fossil-based sources. Meanwhile, when we're doing this literature review, we added 9 other chemicals to this group because they were in active research area and there were so many publications looking into these chemicals. So we completed this list with 34 chemicals, and then we tried to find all the LCA studies looked into these chemicals. When we collected our studies, we tried to categorize them based on different variables. For example, the country of origin. So these studies that we collected are based on US, Brazil, for example. And feedstocks, the building blocks are coming from different feedstocks such as algae, poplar, rapeseed. There are several conversion methods that we consider: pyrolysis, gasification, fermentation, and different scopes. So we tried to categorize the studies based on whether they consider short-term carbon storage, direct or indirect land use change. And finally, we looked into different allocation methods. So it could be mass-based, economic-based, or system expansion. So this is a simple illustration of how we selected each cases for our study. This is a schematic view of a biorefinery. So we have cellulosic biomass as our source, different conversion methods, and different products. So if we consider acetic acid as our target product, we see that it can be produced from lignocellulosic biomass that can have a wide variety of different feedstocks, and we can have 2 conversion pathways for production of acetic acid, and on the other hand, we can allocate the burden for acetic acid compared to other co-products based on different allocation methods. So, and we added another variable, which was the country of origin. For example, this can be softwood from Sweden. So this is how we selected our cases. For example, here we might have 2 cases for production of acetic acid. And then on study assumptions, we collected our studies based on both academic literature and industrial reports. And all the selected LCAs are cradle to gate. The functional unit for all of them are 1 kilogram of target chemical. Current conversion techniques were the only routes that we considered here, so we didn't consider any kind of further technological development or what will be the long-term GHG potential reduction for these chemicals. And we did the GHG reduction potential calculation based on comparative studies, so it means that the studies that we collected at the first place did the comparison between bio-based and fossil-based counterpart, so we just extracted the results. And for those that didn't do this kind of comparative analysis, we used eco-invergenic processes for estimation of the GHG emission of fossil-based counterparts. And so these are the main assumptions we had for our literature review. Now I'm going to show you the number of LCA cases versus the year that we found. I wanted to show you the RFS initiation program and RFS 2 publication date to give you a trend of the number of cases that we found in this literature review. And these cases were about 84 LCA cases for the chemicals I showed you earlier. One of the other parameters that we looked into besides the GHG emission was non-renewable energy consumption for these chemicals. So this figure shows the non-renewable energy consumption versus GHG emissions for each kilogram of the chemicals we looked into. And the orange dots shows the lignin-based chemicals, and the blue dots shows the sugar-based chemical. And as you can see, there is a linear relationship between these two. And as we expected, when the non-renewable energy consumption increases for production of the chemicals, or the whole process is up to distribution, the GHG emission will go up. Now let's take a look at the collective results that we had. This figure shows the percent change in GHG emission for each of the chemicals that we looked into. The blue dots shows the average value for the for each of the chemicals, and the arrow bars shows the range of the data that we found. While the red triangles shows the chemicals that we didn't find any study for them. This line shows the 50% threshold that we consider. And as you can see, bio-based chemicals like succinic acid, like polyhydroxybutyrate, xylitol, and polylactic acid shows an average value below 50% threshold. But the base cases are the ones that have the whole range beneath this threshold. So, for example, succinic acid is one of the chemicals that for all of the studied cases we found more than 50% reduction compared to the fossil-based counterpart. And here is the same results for the lignin-based chemicals. And you can see that these four chemicals are the ones that we couldn't find any study for them. And chemicals like methanol, styrene, PLA shows less than, more than 50% reduction on average. But the point is, there are not many studies looking into the lignin-based chemicals. So for most of these chemicals, you can see that they are single values reported because we couldn't find that many studies looking into them. And some chemicals like phenol and acetic acid are the ones that have been studied much more. On the conclusion side, I want to mention that the sugar-based chemicals, as I have mentioned earlier, have been studied more thoroughly, while there are very low number of studies looking into the lignin-based ones. 8 out of 20 selected sugar-based chemicals showed more than 50% reduction on average, and 5 out of 40 selected lignin-based chemicals showed more than 50% GHG reduction. 7 out of 34 selected chemicals have not been studied so far, because we couldn't find any study for them. And the succinic acid is the only chemical showing more than 50% reduction in all the studied cases. That were 8 cases we found for this chemical. On next step, I'm trying to do Aspen simulations for sugar-based and lignin-based chemicals that have not been studied so far, because during literature review I found so many publications about the routes and the processes that that can be used for production of these chemicals, but really none of them looked into the LCA study and LCA side of that. We are trying to consider other environmental impacts other than GHG emissions, especially eutrophication and pesticide toxicity, which are one of the main negative derivatives from bio-based chemicals. And we're trying to conduct a harmonization study to find more thorough results. At the end, I want to acknowledge NSF for funding my trip, my advisor, Professor Eckelman, and our collaborator, Professor Khanna from University of Pittsburgh. Thank you for your time, and I'd be happy to take any questions or recommendations.
Any questions? So, just a general question about all the folks you studied. Do they all have obvious fossil-based counterparts? I would imagine for some of them, identifying the baseline is not straightforward.
Yeah, the counterparts that we found was, for example, for comparative analysis that we found, they reported their fossil-based counterpart in their own analysis. And for those that we didn't find, I looked to literatures and tried to find literatures kind of correlating these two chemicals, that what would be the fossil-based counterpart, and then I used the Eckelman unit process for estimation of that.
Can I have a quick follow-up then? So, for some of these, I would imagine different studies for the same chemical identified different counterparts. When you showed the percent reduction, is that with a changing baseline just based on whatever that study said, or did you pick one that you thought was sort of the most appropriate?
No, the range that I've shown for each of the chemicals are based on the categorical variables I've shown. So for example, for succinic acid, we can have different cases with different conversion methods or different allocation methods. So the results I've shown was an average value for all the LCA studies and a range for all the data that we have.
So that's more in terms of the basics. So for example, for PLA, there's different plastics it can replace, and different studies have had a different replacing different plastics. So when you the percent reduction, did you choose one specific fossil plastic, or did you use whatever each individual?
Yeah, I used just one counterpart for all of them. So I tried to collect the studies that have the same counterpart, so just to be consistent with the results.
Okay.
Yeah, very, very interesting, and actually very, very important. I'm curious, you referred earlier on about some of your assumptions around, and particularly around allocation. I'm interested to understand, many of these could be co-products in a biorefinery, and how do you handle the allocation issue in those cases? Did you defer to what the reference study used? Yeah,
actually what I did was just use different assumptions that the study used. For example, for the ranges that I've shown, they could use mass-based allocation, economy-based allocation, or system expansion. So I just used whatever the reference used, and showed them in the range.
I imagine that probably was one of the big factors contributing to the variation in those figures.
Yeah. Yeah, actually we didn't look into, for example, one of these variables change our results more significantly, or one of the most sensitive parameters between them, but I think it will be a good point to look into.
Yeah, just a further comment on that is with the fuel standard, there is a defined method of allocation for the fuels. So to require that the full range of a feedstock meet that threshold is maybe a little too stringent a requirement, especially since the fuel standard does allow for a lower burden.
Yeah. Yeah, since we tried to look into different variables, we included that, but I think, yeah, we can, just to be consistent, we can consider just one allocation method.
Well, if you're going to compare it with the, I think you've got a ton of really interesting work here to explore. But if you want to be consistent with that comparison with the fuel standard, I think you need to also be consistent with the allocation.
Yeah.
If that's the direction you're going to go.
Yeah. Yeah, I will include that in further. Thank you so much.
All right. Well, thank our speakers. Thank you to all of us today. And enjoy a break. Come back here at 10:30.